Hello, everyone. My name is Dr. Christopher Moore, and I'm a research associate at West Virginia University, and I lead the day-to-day operations of our grant-funded pollution prevention team. Our team provides no-cost pollution prevention assessments and other related technical support to businesses within West Virginia. Today, I'll be presenting the final webinar of our five-part series covering the EPA national emphasis areas, and that will be pollution prevention best practices for the metal manufacturing and fabrication industries. So just to outline what we'll be discussing in this webinar, I'll first provide a brief introduction into pollution prevention as defined by the Environmental Protection Agency, and I'll discuss which activities are and aren't considered pollution prevention. Next, I'll discuss EPA's national emphasis areas, which are prioritized industries under EPA's pollution prevention initiative. The main focus of this webinar, however, will be the fifth national emphasis area, metal manufacturing and fabrication. I'll provide some background into the industry, then cover several pollution prevention best practices that can be implemented by facilities within these industries to minimize their environmental impact and cut pollution at the source. Then, after a brief summary, I'll do my best to answer any questions you have. If you have questions along the way, feel free to send them in the chat and I will address them after the presentation. So before diving into the topic of pollution prevention, first we need to understand pollution. Pollution, according to the Oxford Dictionary, is the introduction into the environment of a substance or thing that has harmful or poisonous effects. Pollution has far-reaching consequences, not only affecting human health, but also disrupting ecosystems and threatening biodiversity. Given these impacts, it's clear that immediate action is needed to reduce pollution and its adverse effects. Now, pollution prevention, as defined by the United States Environmental Protection Agency, refers to any practice that reduces, eliminates, or prevents pollution at its source before it is created. This approach differs from pollution control, which typically deals with managing pollution after it has been generated. Instead, P2 focuses on proactive steps to prevent waste and pollution from occurring in the first place. This hierarchy of pollution management shows a step-by-step approach to managing pollution, starting with the most desirable outcomes, or the most desirable actions at the top, and moving down to the least preferred options at the bottom. So, when possible, the creation of pollution should be prevented in the first place. If the creation of a pollutant can't be completely prevented, the next objective should be to reduce the amount that is created. When the amount of a pollutant can't be feasibly reduced, options to reuse or recycle should be explored. The next step, recover, refers to the process of extracting any useful material or energy from the waste. The least preferred option is disposal, where the waste will go to a landfill or otherwise be released out into the environment. EPA's Pollution Prevention Initiative emphasizes this hierarchy, encouraging a primary goal of preventing and reducing pollution at its source. So these top two levels of the hierarchy. So as a part of EPA's Pollution Prevention Initiative, in 2015, several priority sectors known as national emphasis areas were identified. These 6 sectors were identified as priorities by the EPA Pollution Prevention Program to focus resources and efforts for maximum environmental and economic impact. These sectors offer substantial P2 opportunities and create a focused approach that allows for better resource allocation and the ability to share successful strategies across similar industries. The original 5 NEAs were the food and beverage, manufacturing and processing industry, chemical manufacturing, processing and formulation. Third is automotive manufacturing and maintenance. Fourth is aerospace product and parts manufacturing and maintenance. And NEA number 5 is metal manufacturing and fabrication. A sixth national emphasis area was established several years ago. Instead of focusing on a specific industry sector, the EPA realized the need for assistance with pollution prevention on tribal and native lands within the country. So the focus of the discussion today will be on the fifth national emphasis area, metal manufacturing and fabrication. So the metal manufacturing and fabrication sector includes industries classified under the NAICS industry classification codes, beginning with 331 and 332. In 2020, there were 58,435 establishments within this sector, with about 7% of them, or 4,270, reporting to the toxics release inventory. The chart shows the volume of waste managed by different approaches from 2011 to 2020 within this sector. And in that period, the amount of waste produced showed a decrease. Unfortunately, the amount of waste that was disposed or treated stayed consistent. That means that there is room for improvement using pollution prevention techniques. The metal manufacturing and fabrication sector encompasses a wide range of industries that can be broadly grouped into these 14 different categories. Iron and steel mills and ferroalloy manufacturing, steel product manufacturing from purchased steel, aluminum and alumina production and processing, non-ferrous metal production and processing, foundries, forging and stamping, cutlery and hand tool manufacturing, architectural and structural metals manufacturing, boiler tank and shipping container manufacturing, hardware manufacturing, spring and wire product manufacturing, machine shops, turn product and screw nut and bolt manufacturing, coating, engraving, heat treating, and allied activities, and other fabricated metal product manufacturing. So now that we've explored the diverse landscape of the metal manufacturing and fabrication sector, let's move towards discussing some of the P2 best practices that can be implemented at facilities within this sector. We'll discuss the best practices in 4 groups. First, we'll discuss a couple of best practices related to material and process optimization. After that, we'll cover a few practices related to chemical substitution and safer alternatives. Next, a couple best practices about waste reduction and recovery will be discussed. And we'll wrap up with a couple of best practices related to drag out and quenchant loss reduction. So first, let's get started with material and process optimization. So optimizing materials and processes is a great strategy for improving sustainability. We'll discuss 2 best practices related to material and process optimization that can be implemented in the metal manufacturing and fabrication sector. And those will be, first, utilizing nesting and sheet metal part fabrication. And number 2, identifying opportunities for dry machining. So let's first look at the use of nesting in sheet metal part fabrication. So in the metal manufacturing sector, parts are often cut or punched from rolled sheet metal, but it comes with significant challenges and costs. One major issue is high scrap generation. So due to inefficient cutting patterns and production errors, a substantial amount of material ends up as a waste. Furthermore, this metal waste contributes to pollution and increases the carbon footprint. If recycled, either internally or externally, a significant amount of energy is required to make it usable. On the other hand, if the waste is not properly managed, discarded metal can lead to environmental hazards. Poor planning and outdated manufacturing methods related to sheet metal fabrication often lead to excessive raw material use, high energy consumption, and increased operational expenses. So one way to optimize the sheet metal fabrication process is with the use of nesting. So nesting is a method in which as many parts as possible are strategically arranged on a flat metal sheet to maximize material usage. So let's look at the example on the screen. The image on the left does not utilize nesting. This kind of arrangement is common. It takes very little time to arrange, and it appears more organized. But there's a significant amount of waste. More than 50% of the area of the sheet would have to be scrapped or recycled, and the yield from that sheet is only 23 parts. Now, if we compare this to the image on the right, in this case, the material use is maximized utilizing nesting techniques. Instead of 23 parts, 65 parts were produced from one piece of sheet metal, and less than 10% of the material will be unused. Thus, the production from the process can be more than doubled, with the only expense being additional resources spent planning and tooling for the more complex arrangement. So nesting is an easy technique to implement, has many benefits. First, maximizing use of the material minimizes waste and reduces environmental impact. Less waste that must be recycled or otherwise disposed, and less raw material is used to meet the same production levels. Recycling and disposal both have an environmental impact, so minimizing waste is going to reduce that impact. Next, by optimizing the arrangement, more parts can be produced from the same amount of material. Additionally, nesting can reduce machine idle time and speed up production, improving productivity. Utilizing nesting also provides significant cost savings on both raw material and the recycling or disposal of the waste. So in total, the lower cost and improved productivity of nesting results in significant improvements to overall operational efficiency and profitability. So the next best practice recommendation related to the metal manufacturing and fabrication sector is identifying opportunities to use dry machining. So in this sector, machining fluids play a crucial role in machining processes by cooling and lubricating cutting tools, and this helps prolong tool life and absolve heat-related problems. However, there are drawbacks to these machining fluids. Often, machining fluid use is poorly managed, leading to excessive usage, resulting in unnecessary waste and inefficiency. This directly contributes to higher costs since purchasing, handling, and disposing of these fluids can be expensive. Another major concern is pollution contribution. The chemicals in these fluids can be hazardous if not properly managed. Improper disposal or excessive use of machining fluids can lead to environmental contamination, affecting soil and water quality. And finally, these machining fluids, they can be harmful to workers that are exposed to them. So exposure to machining fluids can cause skin irritation, allergic contact dermatitis, irritation of the eyes, nose, and throat. And in some cases, workers may experience breathing difficulties due to mist or vapor inhalation. So one possible solution is to identify opportunities for dry machining. The dry machining is a concept that relies on advanced tools, techniques, and coatings to eliminate or significantly reduce the need for machining fluids. So the first step in finding opportunities for dry machining is assessing the processes and materials to determine where dry machining can be implemented effectively. So first, we'll ask ourselves, do the materials allow dry machining, or can materials capable of dry machining be implemented instead? So dry machining works best with certain materials like magnesium and titanium, which don't generate excessive heat when machining, or they may react with machining fluids. Additionally, some metal stock can be purchased pre-lubricated, eliminating the need for additional machining fluids. Next, we look at the tools. Do the tools we use allow dry machining, or can tools that enable dry machining be implemented? Tools with advanced coatings like diamond-like carbon or titanium nitride can withstand higher temperatures without excessive wear, minimizing the need for machining fluids. While these tools may cost more than their non-specialized counterparts, the savings in machining fluids and related costs of their use will exceed the additional costs of the tools, providing an overall savings. Next, we want to look at the process themselves. Can the process accommodate dry machining, or can the process be modified to accommodate dry machining? So making changes to the cutting speed or feed rate, for example, can enhance efficiency and minimize or eliminate the need for lubrication. And finally, keep your eyes out for new technologies and methods. High-speed machining, minimal quantity lubrication, and cryogenic cooling are methods that can reduce or eliminate the need for machining fluids. So we want to just look at every part of the process and see if it can be updated to allow dry machining. So reducing or eliminating the use of machining fluids by implementing dry machining techniques has several benefits. First, eliminating machining fluid waste enhances sustainability and reduces environmental impact. The reduced waste also means that regulatory compliance will be easier. Also, reducing or eliminating the use of machining fluids can improve worker safety. Since exposure to these fluids can be harmful to the workers, reducing or eliminating the use will also minimize or eliminate the risk of exposure to the workers. And finally, proper implementation of dry machining techniques can reduce overall costs. There'll be reduced costs for purchasing fresh machining fluids along with disposal of the used fluids. However, a full assessment of any changes should be performed to determine the financial outcomes. So moving on, next we'll discuss a few P2 best practices related to chemical substitution and safer alternatives that may apply to industries in the metal manufacturing and fabrication sector. So the three best practices that we'll discuss are avoiding dichloromethane-based products, replacing xylene with Oxol 100, and using jet vapor deposition in place of chemical vapor deposition or electroplating. So the first recommendation in this section is avoiding dichloromethane-based products. Dichloromethane, or DCM, is commonly used for paint stripping and metal cleaning within these industries and is also used in aerosol propellants. However, dichloromethane and products that contain it present serious risks to both human health and the environment. These products tend to evaporate quickly, and inhalation can cause acute and chronic effects on the central nervous system. Workers exposed to dichloromethane may experience dizziness, headaches, nausea, and in cases of high-level prolonged exposure, even unconsciousness or death. Additionally, DCM is classified as a likely carcinogen, meaning long-term exposure can increase the risk of cancer, making it a significant occupational hazard. Another critical issue is its contribution to volatile organic compounds, which contributes to air pollution and can cause respiratory problems. So fortunately, there are safer alternatives to dichloromethane-based products for most, if not all, applications. When using dichloromethane-based products for cleaning, a couple of alternatives are aqueous-based cleaning products or the use of mechanical cleaning methods. The aqueous-based cleaning systems use water-based solutions with detergents instead of hazardous solvents. These products pose little to no risk to workers and have no toxic emissions while maintaining effective cleaning performance. Alternatively, mechanical cleaning methods such as media blasting, ultrasonic cleaning, and high-pressure water jets can remove contaminants without the need for chemical solvents, improving safety and reducing waste. For other applications of DCM-based products, process modifications can help eliminate the need for DCM entirely. This includes using pre-coated materials, advanced surface treatments, and other state-of-the-art laser products and methods to achieve the same results without relying on harmful chemicals. So there are several benefits to making the switch from dichloromethane-based products to safer alternatives like aqueous-based cleaners, mechanical cleaning methods, or other advanced products or methods. First, sustainability can be improved by reducing toxic waste and harmful emissions. Next, these alternative methods are safer for the health of the workers. By eliminating dichloromethane use, the workers are not at risk of its harmful and potentially carcinogenic effects. Next, while adapting the processes to these improved methods may have some initial costs, there will also be cost savings due to reduced chemical and product purchase costs and minimized disposal costs. Additionally, elimination of hazardous substances makes regulatory compliance less burdensome and can help businesses avoid potential fines or restrictions. And finally, by eliminating the use of a product classified as a volatile organic compound, emissions and air pollution will be reduced. This is going to lead to cleaner air and safer ecosystems and protect the environment. So transitioning away from dichloromethane is a smart, responsible choice for businesses, and that can improve their productivity and can protect their workers and the planet. So next, let's discuss replacing xylene with Oxol 100. So xylene is commonly used and has many common uses in the metal manufacturing and fabrication sector. It can act as a thinning agent to adjust the viscosity of coatings to ensure a smooth and consistent finish. It can be used to dissolve resins in coatings, improving adhesion and increasing durability of the coating. And it can be used as a cleaning agent, among other applications. However, xylene poses significant health and safety risks. Xylene is a volatile organic compound and evaporates quickly, having both health and environmental consequences. As far as the effects on human health, high-level acute exposure to the vapors can cause dizziness, headaches, and respiratory issues. Prolonged exposure can cause long-term neurological effects, including memory loss and difficulty concentrating. And additionally, xylene is highly flammable, posing a risk to the workers and facility if not handled properly. Like other volatile organic compounds, the emissions from xylene, especially in large quantities, can lead to air pollution and environmental harm. So these risks make xylene use hazardous, requiring appropriate storage, careful handling, and proper disposal. So in many applications, xylene can be replaced with a safer alternative, such as Rust-Oleum's Oxol 100. So Oxol is a safe and effective alternative to xylene, offering the same performance without the health and environmental risks. It's highly versatile, making it suitable for paints, coatings, adhesives, resins, and sealants. It's also an EPA-exempt solvent, meaning it has no ozone-depleting effects and significantly reduces VOC emissions. And additionally, it has a higher flash point than xylene, which reduces the fire risk, making the workplace safer for the workers. So switching from xylene to a safer alternative like Oxol 100 has several benefits. The product is safer for workers as it reduces exposure to toxic fumes and minimizes the risk of health effects like respiratory issues and neurological effects. Second, lower hazardous waste disposal costs and reduced safety measures needed for handling of the product mean there is potential for cost savings. Third, since Oxol is EPA exempt, making the change will help industries meet air quality standards and safety regulations. And finally, Oxol is a low VOC formula with reduced VOC emissions. So by replacing ozone-depleting chemicals with low VOC alternatives like Oxol, the environmental impact is going to be reduced. So Oxol is more expensive than xylene, but the cost savings benefits may outweigh the additional costs. And there are other significant benefits that are hard to place a value on, like the safety of your workers and regulatory compliance. So next, we'll talk about the use of jet vapor deposition as an alternative to chemical vapor deposition or electroplating. So These three techniques, jet vapor deposition, chemical vapor deposition, and electroplating, are all techniques of applying coatings to metal surfaces, with electroplating and chemical vapor deposition being the more common traditional techniques. Electroplating uses an electric current through a liquid electrolyte solution that contains metal ions to deposit the coating onto the submerged part. While chemical vapor deposition, on the other hand, uses chemical reactions of gaseous precursors on a heated substrate in a controlled or vacuum atmosphere to deposit a coating on the part. Each of these methods have associated risks. So electroplating baths need to be changed regularly to maintain quality of the finish. Regularly changing the bath generates significant amounts of hazardous waste that must be managed properly. This involves either on-site treatment where solids are removed and recycled or disposed, and liquid waste is treated and reused or disposed. Or the waste can be sent off-site to a treatment facility at a cost. On the other hand, waste from chemical vapor deposition is much less voluminous, comprised of unused precursor gases and reaction byproducts. However, this waste must also be managed to avoid air pollution and other hazards. Then with each of these processes, there are also hazards to worker safety, as exposure to these toxic substances can lead to respiratory issues, skin irritation, and long-term health effects on prolonged exposure. Additionally, these methods increase air and water contamination risks, impacting both the environment and surrounding communities. And lastly, industries face regulatory and compliance challenges with stricter environmental laws making it harder to manage and dispose of hazardous byproducts. So jet vapor deposition is a coating process that uses a high-speed jet of vaporized material to deposit the coating onto a material in a vacuum or controlled atmosphere. It's a safer alternative to electroplating and chemical vapor deposition. So jet vapor deposition, more specifically, works by first heating and vaporizing a solid material that will ultimately act as the coating. The vaporized material is carried by a high velocity jet of an inert gas such as helium or argon, and the vaporized material is deposited on the component that is to be coated. This is all done in a controlled environment, usually a vacuum chamber, to avoid contamination. And this process results in a high quality, even coating on the component, and it's also highly versatile, making it suitable for various materials and applications. So with reduced chemical waste and lower environmental impact, jet vapor deposition is a more sustainable and worker-friendly solution for advanced manufacturing. It also offers multiple advantages over the traditional coating methods. First, jet vapor deposition enhances worker safety by eliminating exposure to toxic chemicals used in the electroplating process, like hexavalent chromium, cyanide, acids, and other solvents. Hazardous precursor gases used in chemical vapor deposition, like silane, ammonia, and hydrogen chloride, and the hazardous waste associated with each. Next, reduced material and hazardous waste provides a cost savings due to lower disposal costs. Also, since jet vapor deposition produces minimal emissions and generates no hazardous byproducts, regulatory compliance is easier and environmental impact is reduced. And finally, jet vapor deposition can boost productivity with its efficient high-speed coating process, making it a great alternative to traditional coating methods for sustainable and cost-effective manufacturing. So that wraps up that section. Next, we'll talk about waste reduction and recovery. First, we'll talk about implementing an electrolyte recovery system. And after that, we'll discuss electrocoagulation as a method for wastewater treatment. So electrolyte baths are commonly used in the metal manufacturing and fabrication sector. They're composed of a combination of conductive salts, buffers, and other additives in a solvent, often water. They often have they have several applications, including electroplating, anodizing, electroforming, and surface cleaning. But when these baths are changed, the metal contaminated waste must be properly managed. If the waste is not properly managed, it can pose several problems. Improper disposal can cause water pollution, as the metals can contaminate local water systems and harm aquatic life. This leads to ecological damage, as the toxic metals disrupt ecosystems and can bioaccumulate in organisms. Additionally, the metal contamination in the electrolyte bath are valuable resources, which, when disposed, cannot be recovered or reused. And furthermore, improper disposal can result in cleanup costs, fines, or other legal consequences for not maintaining regulatory compliance. So addressing these issues is crucial for environmental protection and staying within legal requirements. So while replacing electrolyte baths with alternative solutions that eliminate the risks is the ideal solution, when that is not possible, facilities should identify ways to optimize the process. Instead of disposing of the electrolyte baths when they become ineffective, there are several methods of electrolyte recovery that can be implemented to recover the metal contamination and process the electrolyte bath, either for reuse or for safer disposal. Some examples of those recovery methods are electrowinning, electrorefining, and membrane-based systems. So we're going to focus in this section on electrowinning though. So electrowinning is an effective method to remove the metal contamination from electrolyte bath. In the electrowinning process, an electrical current is passed from an inert anode through the electrolyte bath containing dissolved metal ions. It is a process where an electrical current is passed to a leach solution containing dissolved metal ions. And as the current passes through the liquid, a reduction reaction occurs where the metal ions are reduced and deposited as solid metal onto the cathode. This is similar to the electroplating process. The metal can then be recovered from the surface of the cathode. So this technique is widely used for extracting metals from solutions, especially in industries like mining and metal finishing. In the context of metal-contaminated electrolyte baths, electrowinning helps recover valuable metals while also cleaning the solvent/water, making it a helpful method in managing industrial waste and reducing environmental pollution. So an electrolyte recovery system utilizing a method like electrowinning will provide several benefits. First, by recovering the valuable metals, the need for raw material extraction is reduced. Next, the recovered materials can be reused in the manufacturing process. The need for replacing electrolyte baths will be reduced, and disposal costs will be reduced, leading to cost savings. Additionally, an electrolyte recovery system helps ensure regulatory compliance by removing contaminants from the waste, meeting environmental standards, and protecting the environment by preventing metal pollution. And furthermore, they save resources, as there will be a reduced need for raw materials, as well as a reduced need for solvents, whether that's just water used as a solvent or a solvent that must be purchased as a product. All in all, an electrolyte recovery system can save money while reducing environmental impact. So while water-based electrolyte baths can generate a significant amount of contaminated wastewater, they are far from the only process that use water and generates contaminated wastewater in these sectors. Contaminated wastewater is generated during cleaning, machining, plating, and coating processes, among others. Therefore, treating the wastewater using a method like electrocoagulation can extend the life of the water and make management of the wastewater easier. The wastewater from the metal manufacturing and fabrication sector presents several serious challenges. First, it contains a high level of contaminants, including harmful metals like potentially lead, chromium, and cadmium, which can pollute water systems. Next, the excessive water consumption can put additional strain on local water sources, especially in areas that are prone to drought. And improper management or disposal of wastewater can lead to ecological damage, disrupting aquatic ecosystems and harming wildlife, and can result in regulatory compliance issues, culminating in cleanup costs, fines, or other legal consequences. So one potential solution, as I mentioned, is using electrocoagulation. And that's a process that uses electrical currents to remove impurities from wastewater. So in electrocoagulation, again, similar to the last recommendation, we're going to rely on an electrical current applied to an cathode or an anode and a cathode in the water, and that electrical current is going to cause the contaminants to coagulate and form larger particles, which can be allowed to either settle out and removed through that process, or they can be filtered out more easily. The electrocoagulation process helps eliminate harmful metals and other pollutants, improving water quality and reducing environmental impact. It's a powerful tool for industries to treat wastewater efficiently while meeting regulatory standards and protecting local water systems. And like the others, electrocoagulation has several benefits. First, it supports sustainable manufacturing by efficiently treating wastewater, reducing the need for fresh water, and minimizing environmental impact. This process leads to significant cost savings by lowering water treatment and waste disposal costs. It also helps ensure regulatory compliance as it effectively removes contaminants from wastewater, helping meet water quality standards. And most importantly, electrocoagulation protects the environment by reducing water pollution, preventing harmful metals and chemicals from entering local ecosystems, and contributing to overall environmental preservation. So the final section of this webinar will be a discussion of best practices related to drag out. First, we'll discuss the development of a drag out management plan. And to wrap up the webinar, we'll discuss a specific type of drag out, quenchant drag out. So let's first discuss the development of a drag out management. So drag out is a common issue in the metal manufacturing sector. And drag out occurs when chemicals from baths are unintentionally carried out with the metal parts that are being treated with the bath. So when drag out occurs, the chemicals that are removed with the metal are wasted, resulting in the loss of valuable chemicals that need to be replaced. When a part must go through multiple different types of baths in succession, the drag out from one bath can contaminate the next bath, decreasing its usable life and potentially affecting the final finish of the part. And as a result, water usage and chemical usage will increase, driving up operational costs. And furthermore, improper disposal of this waste has a significant environmental impact, contributing to water pollution and posing risks to ecosystems. So the solution here is developing and implementing a drag out management plan, and that can help avoid many of these issues. So there are several strategies that can be utilized in a drag out management plan, including the following. Drag out time can be increased. This allows the chemicals to drip into the bath itself for a longer period, minimizing the amount of chemicals lost. Another effective strategy is product modification. So if the product can be modified in such a way that there are fewer recesses or irregular shapes or other areas where where liquids can be trapped, where the fluid can be trapped. If you can get rid of those or minimize those, you're going to be able to minimize the drag out as well. So another option is installing drain boards and drip guards. These can be installed around the tanks to help catch excess chemicals and prevent them from dripping outside of the bath. And similarly, drip bars can be installed to catch the drag out and direct it back into the tank, ensuring that the chemicals are recaptured. And finally, the mechanization of the drag out process can be used to control drag out by using an automated system to efficiently recover and recycle the chemicals. So this is just a few possible strategies toward drag out management. These strategies can be combined when appropriate to further minimize drag out. Okay. So by implementing an effective drag out management plan, you'll find several benefits. First, by reducing chemical waste and enhancing the efficiency of the process, the change promotes sustainable manufacturing. There are also significant cost savings due to reducing the need for new chemicals and lowering waste disposal costs. And also, a drag out management plan supports environmental protection by reducing pollution and conserving resources, particularly valuable chemicals, which are recovered and reused. And finally, let's talk briefly about a specific type of drag out called quenchant drag out. So quenching is a process where a metal or alloy that has been heated is cooled quickly, causing it to harden and achieve more desirable mechanical properties. And quenchants are the fluid that the metal or alloy parts are submerged in to provide that quick cooling. Now, water alone is not a great quenchant because it allows the cooling to happen too quickly, which can lead to cracking in some metals and some undesirable mechanical properties. So most quenchants are either polymer-based chemicals that are mixed in with water or mineral or synthetic oils. So like other types of chemical baths, quenching is prone to issues with drag out. While the risks are similar to other drag out related issues, there are some differences. So the risks are similar to other types of drag out. There are risks of contamination of subsequent rinsing or cleaning baths, necessitating more frequent replacement, leading to increased waste generation and higher disposal costs. Additionally, chemicals lost to drag out must be replenished with new chemicals. So chemicals lost to drag out are wasted resources. However, several factors make quenchant drag out a more serious and costly issue. First, the volume of quenchant fluid needed and the associated costs make these chemical losses more costly than most other types of chemical baths. Additionally, the composition of the quenchant, polymers or oils, can be hazardous if not managed properly, meaning an increased risk to workers and to the environment. And the potential solutions here are also similar to managing other types of drag out, with the primary objective being to keep or return the quenchant solution remaining on the parts back to the quenchant bath. These practices include steps like increasing the drain time by allowing the part to hang over the bath for a longer period after removal. More of the quenchant will drain back into the bath. Reducing removal speed is another option. Reducing the removal speed allows more quenchant to drain from the part, and it also reduces turbulence in the fluid, which can reduce the risk of splashing. Next, consider how the part is oriented in the bath. If any dips, recesses, or channels that would hold quenchant solution can be placed facing downward during removal, the quenchant will be allowed to drain out instead of being carried into and contaminating the subsequent bath. Some of the practices that can be incorporated to reduce the Also, we can use replace racks or replace draining trays with racks, reducing the surface contact area and providing less space for quenchant solution to dwell. If using an oil-based quenchant, using a less viscous polymer-based quenchant instead can reduce the amount of quenchant that clings to the parts. If employees are manually removing the parts from the quenchant solution and controlling their movement to subsequent steps of the processes, administrative controls such as handling guidelines and employee training can be helpful to reduce the amount of drag out and waste. So each of these changes can be applied individually or in combination to help reduce quenchant drag out, providing many benefits to the facility, including uh, by reducing drag out contamination to subsequent baths. Those baths will need to be changed less often, lowering waste disposal costs. It also enhances process efficiency, as changing baths less often can reduce downtime in the process. The reduction in chemical waste supports environmental protection by decreasing pollution and conserving valuable resources. And additionally, by saving quenchant, industries can achieve resource savings, reducing the need for purchasing new chemicals. And finally, reducing drag out helps to ensure regulatory compliance as companies can meet stringent environmental standards, avoiding fines and penalties. So in this session, we discussed several P2 best practices that can be implemented in industries within the metal manufacturing and fabrication sector. Some of these best practices may also be applicable outside of that sector as well. These best practices can help you save money, improve worker safety, and protect the environment, ultimately contributing to a more profitable and sustainable business. So I hope that within this webinar, you found something useful that will help improve the sustainability of your business or help you improve the sustainability of another business. So if you'd like any more information on these best practices, including technical assistance, you can reach out to myself, Dr. Chris Moore, at chris.moore@mail.wvu.edu, or you can reach out to Dr. Ashish Nimbarke at ashish.nimbarke@mail.wvu.edu. Also, please feel free to reach out to us for any other information or assistance related to pollution prevention as it applies to the NEAs or other industries, and we'll do our best to help you. So this slide has the references that we used for this presentation. And at this point, I'd like to open the floor for any questions. Okay. All right, if there are no questions, I'll go ahead and end this session then. I'd like to thank you all for your time and I wish you all a great day. Thank you.